Good morning. Hope I am audible.
Yes, sir.
Presentation தெரியுது இல்லையா? ஆமா. ஸ்லைடு தெரியுது இல்லையா? ஓகே. இன்னைக்கு நம்ம டாபிக் வந்துட்டு டைட்டானியம் வெல்டிங் அண்ட் காப்பர் வெல்டிங். ஓகே. இது ரெண்டுமே நான் ஃபெரஸ் மெட்டீரியல். ஓகேங்களா? இல்லை ஸ்டீல் கிடையாது, ஸ்டீல் ஃபேமிலி இல்லை, இது நான் ஃபெரஸ் ஃபேமிலி, அயன் இல்லாத ஃபேமிலி இந்த மெட்டீரியல். ஓகே, இது எப்படி வெல்டு பண்றது அப்படிங்கிறத நம்ம இந்த கிளாஸ்ல பார்க்கலாம். ரைட், ஃபர்ஸ்ட் டைட்டானியம் வெல்டிங் பத்தி பார்ப்போம். டைட்டானியத்தை பற்றி முதல்ல நம்ம ஒரு இன்ட்ரோடக்ஷன், அந்த மெட்டீரியலுடைய ப்ராப்பர்ட்டிஸ், கேரக்டரிஸ்டிக்ஸ், அப்புறம் என்னென்ன மாதிரி வெல்டிங்கில் பண்ணலாம் அப்படிங்கிறதையும் பார்ப்போம். அதில் என்னென்ன ப்ரிகாஷன்ஸ், எங்கே யூஸ் ஆகுது அப்படி. ஓகே, டைட்டானியம் வந்து சில்வர் கலர்டு மெட்டீரியல், ஹைலி ரியாக்டிவ்னா ஆக்சிஜனோட ஈஸியாக சேர்ந்துடும். ஓகே, ஒரு எக்ஸாட்டிக் மெட்டீரியல் இது. அட்வான்டேஜ் என்னன்னு பார்த்தா ஸ்பெசிஃபிக் ஸ்ட்ரென்த் வந்து ரொம்ப ஜாஸ்தி. மாடுலர் ஆஃப் ரிஜிடிட்டி இஸ் ஆல்சோ ஹை. Toughness is also good. Low temperature application. Very good corrosion resistance. Fatigue resistance is also good. Right? It is lighter than steel. That's a major advantage. Steel 7.86 gram per cc is 4.5 gram per cc. Major advantage. Light metal, high strength, good toughness. Modular of rigidity is also good. Corrosion resistance, fatigue resistance. இதனால தான் இந்த அப்ளிகேஷன்ஸ் எல்லாம், கிரிட்டிக்கல் அப்ளிகேஷன்ஸுக்கு டைட்டானியம் பிகம்ஸ் a candidate material. ரைட், லிமிட்டேஷன்லாம் பார்த்தீங்கன்னா ஹை டெம்பரேச்சரில் ரியாக்டிவிட்டி 430 450 ப்ளஸ்லாம் ரியாக்டிவிட்டி இருக்கும். இது ஒரு லிமிட்டேஷன். காஸ்ட் ஆஃப் மெட்டீரியல் இஸ் ஆல்சோ ஹை. அப்புறம் ஸ்டீலோட ஆர் அதர் மெட்டீரியலோட ஃபியூஷன் வெல்டிங் பண்ண முடியாது. மேபி யூ ஹேவ் டு கோ டு தி அதர் ப்ராசஸ். ரைட், இது சம் ஆஃப் தி லிமிட்டேஷன்ஸ். ஓகே, இது ஒரு சம்மரி. டென்சிட்டி சொன்னேன் 4.5 4.1 கிராம் பர் சிசின்னு. ஸ்ட்ரென்த்து பாருங்க, அன்யீல்டு டைட்டானியம் இஸ் ஒன்லி 186 மெகா பாஸ்கல் ஈல்டு. ஓகே, ஆல்ஃபா அலாய் பியூர் அலுமினியத்தோட we add 5% அலுமினியம், 2.5% tin. This is called the alpha alloy. இதோட yield strength 827. So there is another alloy called the alpha beta alloy. இதுல வந்து அலுமினியம் 6%, 4% vanadium. See the yield strength, it is 1034 megapascal. Right? There is one more alloy is called the beta alloy. Titanium, vanadium, chromium, aluminum. Strength is 138 megapascal. ஒரு முக்கியமான பாயிண்ட், இது வந்து அலக்ட்ரோபிக். நம்ம ஸ்டீல் பார்த்தோம் பார்த்தீங்கன்னா, அயன் கார்பன் டயக்ராம் ஜஸ்ட் ரெஃப்ரெஷ் பண்ணிக்கோங்க. ஆல்ஃபா அயன், பீட்டா அயன் சொன்ன மாதிரி, இது வந்துட்டு ரூம் டெம்பரேச்சர்ல இட் இஸ் ஆல்ஃபா. ரைட், இஃப் யூ ஹீட் இட் கோ டு பீட்டா. இட் இஸ் அன் அலக்ட்ரோபிக் மெட்டீரியல். தட் இஸ் ஆல்சோ அன் அட்வான்டேஜ். ரைட், அதனாலதான் இதெல்லாம் ஏஜிங், சொல்யூஷன் ட்ரீட்டிங் இதெல்லாம் பண்ண முடியுது. அது பண்ண முடியாது, ஒரே ஸ்ட்ரக்சர்ல தான் இருந்துச்சுன்னா நம்ம இந்த வேலையை பண்ண முடியாது. ரைட், so this I have already seen. Okay, corrosion resistance, especially sea water, it's good. Acid solution will have high oxidation resistance. It's having a good resistance to corrosion. Right, application, critical applications, aerospace, defense, marine, chemical processing equipment, surgical implants, power generating plants, sports equipment. Light, corrosion resistance, good fatigue, high strength, all these calls for critical applications in these areas. Right, aerospace, highly loaded components, airframe, component, satellites. These are all some of these areas, especially the fuel tank, engine casing, These are made of titanium alloys. Chemical processing equipment, because of the high corrosion resistance, storage tank, anode basket in the electrolytic process. All these areas, titanium has been widely used. This is some of the applications, right? Where titanium has been used in the aircraft industries, right? Marine application, right? Coming to the alloy system, I told it's commercially pure alloy, pure titanium. We called one category. Next, I said it is alpha alloy, titanium alpha alloy. Another one is called beta alloy. So we have alpha, beta alloys in between. Okay, right? In the alpha, beta form or in the process, we are able to quench it, get the required high hardness, 1038, 1034,000, the range போறதெல்லாமே இத சடலா பஞ்ச் பண்ணி கல்லூரி retain the strength. Okay. So எந்தெந்த எலிமெண்ட் எந்த ஃபேஸஸ் ஸ்டெபிலைஸ் பண்ணுறது? ஆல்ஃபா ஃபேஸை ஸ்டெபிலைஸ் பண்ணுறது அலுமினியம். பீட்டா ஸ்டெபிலைசர்ஸ் பாருங்க, குரோமியம், கொலம்பியம், காப்பர், அயர்ன், மாலி, நிக்கல், palladium, silica, tantalum, tungsten, vanadium, all these things stabilize the beta phase. If you add these, so beta phase is getting widened. Okay. Aluminium வந்து alpha phase increase பண்ணும் area. Neutral tin and zirconium. There are certain interstitial elements: hydrogen, oxygen, nitrogen, carbon. இது வந்துட்டு within this space lattice, atomic level, ரெண்டு ஆட்டமுக்கு டைட்டானியம் ஆட்டமுக்கு இடையில these things will go and sit. Okay. So coming to the specification, ASTM நிறைய கிரேட் இருக்கு. Okay. So aluminum, zirconium, moly, all those things becomes a nominal composition உள்ள alloying element. Right. Look at these impurities level. Iron becomes an impurity here. Oxygen is impurity. Carbon itself is an impurity here. Right. 0.1. Look at these strength levels. It goes from 262 ultimate tensile strength. Now 862, you have 924, you have 986. Right? These are unalloyed, the top one. When we have alpha, near alpha alloys. Alpha alloys, you have the strength goes up to 986. Yield becomes 938. Right? So we have alpha, beta alloys. The strength you see 1117. Okay. So beta alloys 1200, 1241, 1524. We have titanium with the tin 4.5, zirconium 6, moly 11.5. So it goes to this 1524 solution treated and age. Okay. So these are all the advantage. Okay. Because of these solution treatment, we are able to get the required strength. Taking back to the high temperatures and the allotropic form இருக்கிறதுனால, இப்போ allotropic ஃபார்மே இல்லை, ஆல்ஃபால அப்படி ஒரே ஸ்ட்ரக்சர் தான் இருக்கு. There is no use. Right? Coming to the wire, ERTA1, TIG wire, pillar wire, ERTA2, ERTA3, you have carbon, 1.03, oxygen is well be controlled, and these requirements are very much important because this becomes an impurity level. You have to control this. Okay, rest of the things we have matching with respect to the alloy content, right? These are various heat treatment, just for information. I said, solution, treated, and aged. You have to take it to 900 to 970 alpha beta alloys and quench it in water. 1 hour, keep it and quench it in water. Then the strength becomes high. And if you do the aging after that, the specifications will come out. So it becomes, the temperature becomes 480 to 510 for 12 hours. You see aging treatment. Like that, for the beta alloys, the solutionizing treatment temperature is 760 to 850 and so on. Okay. Only for SR, look at these temperatures, right? It is only 480 pure titanium. In the alpha beta alloys, it is only 590. Alpha goes to 640 max. Within this range only, we will have to heat it and do the stress relieving operation. Okay. Coming to the welding part, TIG welding, plasma arc welding, electron beam welding, all these processes it is suitable with respect to the fusion welding route. And coming to the non-solid state welding process, diffusion bonding, superplastic forming, followed by the diffusion bonding. Then the friction welding, explosive bonding. These are all these techniques by which we can do the welding of the titanium and its own alloys. Okay. On the basic requirement in fusion welding process, TIG is the best suited process or electron beam welding by vacuum. Net gas shielding is very much required. Okay. Additional shielding for the solidified metal up to even 430, cool to 350. Beyond 430, this metal starts what reaction with the oxidation. That's why once the weld has been completed, the weld bed should be allowed to cool till up to 350 with the inert gas shielding. That is called the secondary shielding, people used to call, right? The color of the weld indicates the contamination. Where it has reacted with the oxidation and all can be very well seen with the naked eye with the color. This has resulted a brittleness. Okay. Fusion welding with steel or other materials is not possible. That is one of the drawback. Friction welding, explosive and diffusion bonding methods that we have discussed there. We will see in detail. Okay. Coming to the weldability rating, commercially pure titanium grade weldability rating is excellent. Okay. Alpha alloys in certain grades with the palladium, it is excellent, right? Fairly good. Some alpha alloys, near alpha alloys, almost we can do, right? But with manganese alpha beta alloys, it's not recommended. Okay. For certain applications, aluminum moly alloys, alpha beta alloys, right? That is also is little bit difficult, only limited to certain critical applications or special applications, you can say. Whenever you have put A and B, most beta alloys, right? Or even alpha alloys, near alpha alloys, all these weldables are fairly good to excellent. That's the major advantage of using these materials for the welding application. So we'll discuss how we can do with the thick welding, right? Primary shielding, I said, there are two shielding. One is called primary shielding, another one is called secondary shielding. Primary shielding through the thick torch alone is not enough. That's the requirement. You have to go for additional shielding, we call it as the secondary shielding. The solidified hard metal, the weld, and the HI set, not only the weld, the HI set, has to be shielded by the trailing side of the torch. That is, the weld which has been already completed has to be protected from the atmosphere till it is cooled down to 300 degrees centigrade. So we need the shielding. That's called secondary shielding. Root side also, we'll have to do the shielding by the inert gas. These type of shieldings are mandatory in the TIG welding. Okay. So how these can be achieved? All this shielding can be achieved is you can do the welding in the inert atmosphere chamber, the flow purged chamber or in a vacuum purged chamber, or we can do welding in the open air with auxiliary additional shielding. Okay. So this is something with the inert atmosphere chamber. This is called the blue box welding, where we have entire chamber has been air has been removed and inert atmosphere like argon has been pumped in, like our this COVID test, like that the welder has to put his hands inside, take the torch inside, do the welding here. Okay. So by this way, the root, additional shielding, tailings, all these things have been taken care. Okay. This is another setup like that. So wherein with the flow, these are all these inlet and outlet mechanism by which the argon gas has been supplied in. So this is the component by which they are doing the TIG welding. This is the torch you can enable. So the welder has to manipulate the welding after seeing, right? So this entire chamber is filled with argon. Purging has been taken care both for the trailing and as well as for the root arch, right? This is another chamber. This is completely vacuumized, vacuum practice chamber, right? Building as a do the vacuum and the component has been kept inside, right? And the welding has been done. Okay. And coming to our shielding, I said, in case of open air, primary shielding through the thick tar which has been taken care. The secondary shielding is to the trailing shield. As you know, already deposited welding metal has to be protected from the atmosphere. That has been taken care by the trailing shield. This takes care of the solidified metal and the HIZ. Backside welding, and that is for the root welding, root pass protection, right? That is for the grooved backing bar for root bead shielding. The electrode is a thoriated tungsten in the case of TIG welding. Normally, the size will be bigger for the same current rating compared to the ferrous material. Flow rate should always be also higher, right? Use gas lens for the laminar flow. The flow should be laminar, it should not be turbulent, so that the shielding becomes 100% paka. Minimum electrode extension. Normally, you will be knowing that the electrode tip will be protruding outside in the case of TIG welding. So if their length should be kept to the barest minimum, or otherwise there will be a chance of touching this electrode in titanium that becomes getting contaminated. So the minimum extension is required. Use forehand technique, no weaving at all, right? This is what this open air welding with manual TIG. So this is the TIG torch. See the 100% shielding there. This is the trailing shield, what we have been holding. This is the direction of welding from left to right. Okay, so once the welding is progressed like this, the already deposited welder, including the HIZ, has been protected till up to 300 degrees centigrade by means of supplying the argon shielding. This is the one. So since it's a bead or plate welding, underneath there is no purging is required. This is the shield. Okay, this is the another one. It takes care of the pipe welding. This is the trailing shield, which takes care of the deposited welded metal and the HIZ. This is another way. Okay, this is the shielding arrangement setup. Here made separately shown. Here we have an inlet, takes care of the curve, takes care of the common component geometry. Likewise, you have to make the shield. The shield need not be like this alone. We have to be taken care of by the applications of the application and the geometry. This is the typical tip to tube sheet welding, right? Made up of titanium. Tubes inserted here. They have been extensively used for the nuclear steam generators. Okay. So how to detect this contamination? I said, there are some colors by which you can able to identify how this contamination happens. Ineffective shielding, that is the primary shielding, trailing shielding, contaminated shielding gas itself, the base metal and filler metal, right? These things has to be effectively avoided. This is the color by which we have to ensure whether we can able to have proper shielding and all. The colors become shiny silver. You have a good effective trailing shield. No embezzlement will occur. The color becomes gold, like this. Slight contamination is there, right? And it becomes light blue. It is inadequate shielding. Slightly more contamination. Depending upon the application, we can decide with that. Deep blue, embrittlement of the weld, you have to remove it totally. Gray, white, highly brittle. You should not use these. Okay? Clean weld, silver weld. These things are all the contamination. Shielding is not paka. Okay, that is the message. From this, we can able to identify. Okay? This is another view. Light golden straw color bead. Right? The oxygen content is 0.1. It causes a brittleness because of these corners. So this is another one. White tiling shield is not sufficient. It has failed in the bend test because of these brittleness. Okay. Coming to the defect part, contamination due to cracking is caused by the residual stress coupled with a lack of ductility. Right? The interstitial we told some of the elements which gone into the solution in between the titanium atoms like oxygen, nitrogen, carbon, hydrogen. See, oxygen plays a very important role. Its content almost about 3000 ppm cause the cracking in the well. Right? Hydrogen embrittlement and resultant porosity also. Right? So normally pores originate at the trailing edge of the weld pool. Okay? Due to the partitioning effect of the interstitial that is in between the dissolved oxygen and hydrogen. Okay? When generates schools in between it get blocked. That's why it is called the interstitially bonded effect. Right? What's the remedy then? Cleanliness, 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 cleanliness is the only solution. The iron surface has to be cleaned with stainless steel wire brush. Don't use this wire brush for other application. Exclusively separate wire brush has to be cut. That should be made of stainless steel. Okay? It is very much important. Aluminum oxide or silicon, carbide grinding will silicon use. Degrease with acetone, including the filler rod, the areas. Remove all the hydrocarbon. Adequate inert shielding, inert gas shielding till up to 300 degrees centigrade of the deposited weld metal. Most important thing, shielding gas should be restricted with oxygen and moisture content. Ultra pure argon, 99.999, 999 category, 0.99 purity. That much gas cylinder has to be used for the argon. The conventional TIG welding for steel, don't go for that. You go for the when welding that you go for the grade 1 with restriction on the oxygen and the moisture content. Cleaning, cleaning, cleaning is the only mantra for the effective welding of titanium. That is very much important. You should not touch the wire with the bare hand. It is important. This is some of the component. I think you can skip with that. This is the electron beam welded component. These are the electron beam weld. Hybrid bulk head structure fabrication using combination of forming and joining process. Right? You see some of the application is fuel tanks, gas bottle, right? Electron beam welded. That's what we have seen in our earlier pictures where in the glue box welding or done the welding for the defense application. Right? So I said earlier, even the cleaning during the cleaning process, you should not touch the bare with bare hand with either the wire or the material. Ensure the entire system of gas delivery has been leak proof, right? Including the torches till up to the cylinder head. You have to ensure there is no leakages is there, right? It is more important. And the gloves should not be lint free cloth gloves has to be worn. Conventional gloves, there will be certain particles which may add the additional particle, right? Lint free cloth gloves has to be worn. Those things are the precautions, right? Diffusion bonding, a solid phase process, the coalescence of the fairing surface by the application of pressure at a high temperature. No macroscopic deformation, melting, or relative motion of the particle. A solid filler metal may or may not be used. There is a diffusion bonding welding process. You will have seen that. This is the mechanism, right? Initially, we have some contact like that. The first stage deformation and the interfacial boundary formation. Secondary stage, there will be migration and the entire force is getting eliminated. The stage, we have the entire volume of force is eliminated, and you have the proper bonding between these two, right? This is this is one of the components by which we can able to do the diffusion bonding process. This is what the proper design. Okay, this is what this component. This is what this tool details. This is how it has been done. We have a press like this. Okay, right? Put this component inside, evacuate, heat, and press it. You can able to do this component. Okay, this can be reused. This is what these toolings are there to take care of these dimensions. Okay, this is actually the component. This is has been kept inside and do this diffusion bonding, heat it and press it, right? Because of that, these components are getting formed. Then you remove it and you can reuse it. Okay, structure and skip that. Temperature is almost 0.6 to 0.8 times the melting point, right? This is what we have to be done. For alpha beta titanium alloys, it is 75 to 100 degree Fahrenheit above beta transes. Transes is nothing but the critical temperature. Iron carbon diagram you have seen in a lower critical temperature, upper critical temperature, and so on. Here it is only one alpha to beta. The temperature is called the beta transes. Okay, it is always 75 degree Fahrenheit above the beta transes temperature. For titanium aluminum, it is 1825 degrees Fahrenheit. Pressure should be just below the yield point. Okay, time. So parameters are there. Okay, these things has to be followed for this particular process. And the advantage is avoidance of the metallurgical problem. That is one fabrication of the different shape. To the net dimension, what is the first dimensions you can able to maintain? Corrosion resistance is very well maintained, not only for this material, because titanium requirement applications calls for corrosion application, right? Production of thick parts with uniform through thickness properties, that is major advantage. Thick components through thickness properties have been completely ensured. Dissimilar combination can be done with this welding, right? This is one of these stiffened sheet structure fabricated by continuous seam welding by diffusion bonding. This is another panel. This is one of the latest techniques called superplastic forming coupled with diffusion bonding in titanium. Right? It's a two-stage process. Forming usually superplasticity of the titanium alloys at elevated temperature. Then diffusion bonding takes place. The complex shape we can able to obtain by this process. The definition is superplasticity is a phenomenon by which materials are able to achieve an extraordinary elongation without undergoing any necking. That is an advantage, without breaking. Okay, titanium can be elongated to 1000% at temperatures of 926 to 950 degrees centigrade. That is the advantage. That's why we are going for the superplastic forming. Okay, this is one of the components which has been done with superplastic forming. This is the earlier method. You see, 41 parts with 200 fasteners like these bolt nuts, This has been done 2 parts, then do this like that. So this is the engine component for the Boeing 757 aircraft. After the superplastic forming coupled with diffusion bonding, this is the single sheet which has been found. Single sheet, these shapes have been taken care. Let us see how it has been done. This is what this process is. So we have a single sheet, we have two sheets, we have the three sheets, we have the sheet here, titanium, aluminum, vanadium sheet, right? Put these, the reinforced structure in the single sheet has been formed by the superplastic forming. Two sheets, this is the die, and you have these top of pieces, and you have the another one, This is how it has been formed. The top has been joined like this. In this area, this has been formed and the welding has been done. This is the with the sandwich structure with the three sheets. Bottom like the pana shape. In between you have like this. On the top you have so all these three, plate 1, plate 2, plate 3, and we have the top of in between, and the superplastic forming coupled with welding is done here, done here, done here, done here by diffusion bonding. This is the major advantage by which titanium components are being manufactured. This is some of the applications for the aircraft industries, right? Just done with superplastic forming, right? This is for the door panel. I'm going to detail with this superplastic forming, right? This is the landing gear which is formed by superplastic forming, diffusion bonding, actually enable CD welding here, right? Another one is the explosive welding. We have studied that. So we have the unmill, we have the parent material, and we have the another flyer plate, and up over and above that we have the explosive and we have a detonator. So once the detonator has given a fire and the explosives give the required energy, right? And this buffer plate and the flying plate get welded together, right? This is how the structure will be the interface. This is called explosive bonding. Titanium can be done with explosive welding by this method. So this is a titanium clad sheet done by the explosive cladding method. It is steel, right? This is titanium clad plate, how it has been joined. Okay. Explosive forming is another one method. It's very good for the titanium welding. Coming to the friction welding part, all of you would have seen what is friction welding and all. It's a solid state process, please understand. Right? Right? Beginning, the two members are there. Right? We have rotating it in the flash starts forming, and once flash developed and we do the force and the forging takes place. So it is nearer to the melting temperature in the liquid state. We can able to join both the components. Fusion zone is absent, the KZ is very narrow, no need for filler. These are some of the advantages of the study that. And major this one is, it is easy to automate for the mass production. Titanium can be welded with friction. Okay, this is some of these components. Stainless steel to titanium has been done with friction steel welding, friction welding. Right, this is titanium to titanium. It has been welded by the friction welding. This is another advantage by which we can able to do the titanium component. Right? In a nutshell, it is an allotropic. Shielding becomes very much important. Primary, secondary, and root shielding. Right? Strength is very high. Good corrosion resistance. Process is TIG. Able to do with other processes, solid state process like friction welding, explosive welding, super plastic diffusion bonding. Right? And colors indicates whether the weld has been contaminated and so on. Coming to the copper welding, right? It's a highly ductile material. Melting point is very low, but the fun part is thermal and electrical conductivity is very high. Excellent electrical conductivity. Okay? Similar to titanium, the corrosion resistance in certain environment, especially seawater corrosion, this is good. You can able to easily fabricate good strength and fatigue resistance. Right? It is a phase centered cubic structure at room temperature. Density 3 times higher than aluminium. It is about 8.9. Okay, malleability is good, machinability is good. Applications: electrical conductors, thermal insulation, cosmetics, saltwater environment, alkaline solution environment, because it's good corrosion resistance, good electrical conductivity. Those areas this has been widely used. And coming to the alloy system, titanium we have only three pure titanium or alpha, beta, like that. And rather than the strength has been increased due to solution treating. Here, these alloy systems has been devised in such a way that we have pure copper, almost 99.3% of copper. Another one is a high copper, whereas we can add up to 5% of alloying element, right? Another one is called the very famous alloy, copper zinc alloy. We call it as the brass. You have heard about it. Brass is copper zinc alloy. 40% zinc is added, is called copper zinc. Another one is called copper thin alloy. This is called phosphorus bronze. Because tin becomes the primary element, it contains up to 10% tin and up to 2%, 0.2% phosphorus. It's called phosphor bronze. We have pure copper, we have brass, and we have the phosphor bronze, and we have copper aluminium. It is called aluminium bronze. It is called 10% aluminium. Third one is called silicon bronze, phosphorus bronze, aluminium bronze, silicon bronze, which contains 3% silica. And we have copper nickel alloys, is kind up to 30% nickel. And we have copper zinc nickel alloys. We call it as a nickel silver. It's called. It contains 27% zinc and 18% nickel. You need not about memorize all those things, but you can able to identify copper is pure copper. We have the alloyed copper. We have bronze. We have phosphorus bronze, aluminium bronze, silica bronze. And we have copper nickel and nickel silver. These are some of the alloy systems by which copper has been identified. And the unified numbering system CNS, the copper association is given a numbering like this. Starts with the C. C stands for copper. 100 to 100 followed by XX is 100, 0, 0, something like that. 0, 0 is normally omitted here. The other numbers like 11, 12 obviously omitted. Till up to 150 it is called pure copper. 151 to 199 age hardenable copper. 2 series copper zinc alloy is called brass. 3 series 30,000 series is called copper zinc lead alloy is called lead and brass. 4 series is called tin bronze. 5000 series we called copper thin lead is called phosphorus bronze. We said, brass we have lead, we have tin, we have phosphorus. The bronze, copper aluminium is 6 series. And 70,000 series is called copper nickel alloys or copper nickel silver alloys. Likewise, they have been identified. With this number, we can able to identify what type of materials, what is of the alloying element, what is the name of this material, you can able to identify. The questions have been asked. Name of the alloys, the type of brasses, or the aluminum alloys, you can able to identify. And the alloys in the cast structure. This 8000 series is called pure copper. 813 to 828 series is called 95 to 99% copper. 833 to 899 copper zinc alloys. And 9000 series is called other alloys. In the cast form. Okay, this is in the rod form. Right, tube, sheet, and so on. Right? The effect of alloying elements we can quickly rush through. Zinc reduces the weldability. Tin increases the hot cracking. Beryllium, aluminium, nickel, all those things, oxide getting entrapped, which reduces the strength of the weldment. Okay, formation of these oxides are prevented by shielding gas or by fluxing. Okay, silicon beneficial, the deoxidizer, similar to steel. Low thermal conductivity makes silicon bronzes the most weldable copper alloy by arc welding process. phosphorus does not affect, right? Chromium, inert productive atmosphere to prevent formation of chromium oxide. Cadmium, no serious effect. Oxygen causes porosity, reduces strength. Some of the deoxidizing elements, usually phosphorus, silica, aluminum, iron, has been added. Right? This is something with respect to the alloying elements effect. Coming to the weldability part, what are these factors which are getting affected? Effects of thermal conductivity. Copper has a high thermal conductivity, right? The type of current and shielding gas must be selected to provide maximum heat input because heat is immediately dissipated. Preheating is decided based upon the base material thickness. So this thermal conductivity counteracts the rapid heat dissipation. Cold worked copper tends to become weaker and softer at HIZ. Hot cracking may occur. This is during welding. Welding position, highly fluid nature. Flat position is used because the high fluid nature, flat position is maximum wherever possible you have to use. Vertical overhead is rarely used. Okay? Precipitation hardened alloy, beryllium, chromium, boron, nickel, silicon, all those things have been added. That should be taken care of during oxidation. Okay? Properties, reduction in properties, mechanical properties due to over-aging. What is called this precipitation hardening and aging alloy? There are certain elements like these, all this added in this. These comes as the precipitates which enhances the strength. And if you do it overaging, that is kept at the higher temperatures during welding process for some more time during the cooling process, this may reduce the mechanical properties. Should be welded in the annealed condition, followed by the precipitation treatment. This is the solution, right? Because alloys will deteriorate its own mechanical properties because of this aging. Aging certificate, these precipitates will never come back to its original. So it will not form the precipitates. Precipitates is getting broken down. So that is called overaging. So the better process is do it in the annealed condition followed by the precipitation treatment. Hard cracking is another problem associated with copper, copper tin alloy, copper nickel, right? Because there is a wide difference between the solidus to liquidus temperatures. If you look at the iron carbon diagram, something like the alloy system, the difference is very high, right? Severe shrinkage stresses are produced, right? The interdendritic between these dendrites, these liquid metals will start entrapped in between the thin film, which calls for the hard cracking, right? Porosity, zinc, cadmium, have the low melting point, which leads to porosity. Vaporization of these elements also results in porosity. Zinc, vapor, okay? High travel field and filler metals with less volatile element content is the required solution. Surface conditions, oxides formed are very difficult to remove. Cleaning and shielding helps to avoid the oxide formation. Okay? Coming to the real weldability characteristics of these alloys, what you have seen there, like from the pure copper to various brasses and bronzes. Pure copper, high conductivity, requires preheating above 5 mm thickness. Porosity and embrittlement in HAS in a tough pitch copper and porosity in the artesian wells in the phosphor deoxidase copper. You have to preheat beyond 5 mm, right? In the bronzes, zinc vaporization occurs. Brass is an alloy of copper and zinc. The zinc vaporization occurs. This gives the porosity, toxic fumes. Right? Low zinc brass, that is up to 20% is weldable by fusion. And caution is zinc-free filler metal has to be selected. That is the requirement. Normally, bracing is preferred for these brasses or brace welding. Okay. Higher zinc process, very difficult to weld. This is the best method. Tin and phosphorus bronzes, very high hard cracking occurs. Prone to hard crack because these forms the low melting bones for hard cracking. Aluminium bronze, aluminium oxide forms, right? To prevent that, go for the gas shielded process like TIG, with AC or MIG. Low thermal conductivity, no need to preheat for aluminum bronze. Okay, copper beryllium or copper chromium alloys. These are precipitation hardened alloys. As I said, reduction in strength, cracking in the HIZ. Do welding in the solution annealed condition and then do the heat treatment. Cupronickel, single phase alloy, very good weldability, no issue of welding problem, but it is prone for path cracking when there is a presence of sulfur. Control sulfur, right? Then cupronickel is a very good one with respect to the welding point of view, right? And coming to the most important one, the preheat copper, right? This is a very good diagram. Please try to understand this. The effect of the welding process, the shielding gas, and metal thickness decides the preheat requirement. Base metal thickness, in the case of steel welding, thickness higher, you do that, formula is there, all those things and all. Based upon the composition, you can able to appreciate carbon equivalent and all. Here, the process and the shielding gas, this becomes a vital input to decide the preheat temperature. For example, if the plate thickness is say 12 mm, right? If you do with the TIG welding with argon, it's around 425 degrees centigrade is your preheating temperature or 450. But the same TIG welding, sorry, you are doing with helium, you can reduce the preheat to 250. The shielding gas effect has a reduction in the preheating temperature. It is not so in steel welding, right? Carbon equivalent thickness and all. The GMAW argon, you can go with much less preheating temperature. Okay, that is an effect of preheating. That is how you have to select. If you go with argon MIG welding, what is the preheat? TIG welding, you have to increase. And the same TIG welding process, if you go with the helium, there is big properties of these gases. I'm not going to go in detail with that, right? There will be reduction in preheating temperature. Okay, this is unique for this copper welding. Coming to the effect of shielding gas with respect to preheat on the bead effect or the penetration effect, you can see that our helium, this is the penetration, almost a 6 mm thickness, almost 5 mm. You can able to see that, right? In the case of argon, right? If you preheat to 400 degree, then only we can able to do the same 4.6 mm penetration. That's why we said the effect will be more with the helium, or here you have to go with almost 400 degree to achieve the same penetration, right? And if you reduce the preheat temperatures with argon, the penetration comes down. Why? It immediately dissipates the heat. Okay. Coming to the process side, SMAW normally used for maintenance surfacing of the worn-out part. Electrodes are available, ECUSI, ECUS, SMA, and so on. Use DCEP. As I said earlier, do flat position welding. In the case of TIG, argon or argon helium mixtures are used with increased heat input. AC used for aluminum bronze and copper beryllium alloys up to 3.3 mm. Pulsed current can also be used, right, in the TIG welding. Plasma arc welding can be done. Advantage of reduced tungsten inclusion and lower fumes. Why? The tungsten rod is kept inside the, what do you call it, the cup, right, nozzle. It is not protruding outside. TIG, it is protruding outside. Plasma arc welding, it is kept inside, well inside, recessed inside. No inclusion, very good process. GMAW can be done. Argon plus helium mixes for heavier section. Filler is ERCU, spray transfer. Pulse current can be used. Gas welding is used for pure copper, no problem. Another best process is bracing and brace welding. I told, especially for, except for aluminum bronze, they have been used with copper phosphorus. All the alloys you can do the brace welding. right? Copper, zinc, some alloys you can see this 22500, C490, 80, all those things and all. Zinc beams is a problem because we have a zinc, low zinc bronze can be shown to have a good weldability, which is TIG. Preheating is not at all required. Leaded bronzes are unweldable. Shielding helium for alloys with a higher thermal conductivity, right? Filler should not have zinc. The recommended filler is VRCU-SN-A, right? Do the same brass. You can do with the GMAW, right? Filler should not contain same thing. Silicon bronze VRCU, SIA. Good fluid it is because of addition of the silica. Polarity is DCEP, but GMAW have to do the preheat of 95 to 315 for low zinc alloy. High zinc alloy, more porosity is not recommended. Filler is like, okay. SMAW also electrodes are available, different grades are available, low zinc is available, preheating 200 to 260, very much important, right? High zinc copper alloys can be welded with aluminium bronze, electrodes are available, ECUAL-A-A2, you have to go for high zinc, right? Preheat and interface, very much control has to be done. 260 to 370, zinc, copper. These are all some of these techniques we'll have to follow during SMAW. Coming to the phosphorus branch, in the case of TIG, up to 13 mm you can do DCEN or a stabilized alternating current. Each layer has to be short peen, that's very much important. Filling gas is argon. For thicker section, go for helium. Then only you can able to get the penetration we have shown. Filler is ERCUSN-A. Preheating thin section not required. Thick section call for 175 to 200 degrees centigrade. Caution is 200 degrees is the interval. Do preheating, do welding, stop, do welding like that. This is the technique, right? In the case of GMAW for the phosphorus plants, up to 13 mm, single V filler is recommended. Filler is like this. Preheating of the phosphor bronze helps in obtaining a complete fusion, less porosity, but the columnar grains are increasing and it goes to hot cracking. Precautions have to be. That is why is that the preheating and interpass temperature has to be critically controlled. 190 degrees centigrade is very much critical. 170 will have to be the preheat, 190 is the upper limit. SMAW covered electrodes are available. Preheating is 150 to 200. Right? For obtaining the maximum ductility, this can be post weld heat treated to 480 degrees centigrade. Right? GCAW copper nickel alloys up to 1.6 you can do. Use thoriated electrode, argon shielding gas, DCEN or alternate current can be used for automatic welding. Preheating is not required. And the backing strip or rings can be used to support the root pass. Filler metal should be a deoxidized one, which eliminates the porosity and possibility of the oxygen emboldenment. The wire has to be ERCUNI completely deoxidized. Even sometimes this goes by double deoxidation. Okay, autogenous weld can be made up to 1.6 mm thickness. For the same alloy, copper nickel alloy, GMAW is a very good process. Preferred welding process for non-related copper alloy, thickness up to 1.6, only flat position. Gas is argon. Argon, helium mixes give better penetration for thick section. Right? Direct electrode positive is recommended. Spray, filler metals are available. No preheating, no post heating, copper nickel. Interpass should be maintained below 65. That is very much critical. Okay? SMAW is also available. DCEP has to be used, but slab lining is a little bit difficult, but you will have to ensure completely the slab is removed before you deposit for next one. But this process is recommended when we go for this vertical and overhead position. There are some applications you have to go for that. Other welding processes other than the TIG, MIG, plasma, manual welding. These other processes, beam welding, laser beam, Difficulties are high reflection of the laser beam and higher thermal conductivity. Absorption increases with temperature. Shorter wavelength is required. Electron beam welding, both thin and thick section can be done. We can do the resistive spot welding. Lower conductivity alloys can be easily spot welded. Not practical for unalloyed copper. Right? Flash welding we can do. Leaded copper, up to 1% lead can be flash butt welded. Rapid upsetting at minimum pressure. Yesterday we told high strength low alloy steel pressure has to be increased. Here you have to go for the minimum pressure. No melting point and narrow plastic range. Premature termination of the current, lack of fission result. Delayed termination will go for overheating. The parameter setting is very critical. Solid state welding, annealed copper can be welded at room temperature. Good malleability. Diffusion welded or explosive welding is also possible. Right? These are some of these processes. It gives a rating. These are the materials. Materials are there: ETP copper, oxygen free copper, along this UNS number, brass, cadmium copper, lead brass, phosphorus bronze, and so on. Against these, there are so many processes what we have discussed, artificial welding, cigarette metal arc. This I have not discussed. Gas metal arc welding, gas connection arc welding, resistance welding, solid state welding, bracing, soldering, electron beam welding, and all. For each material, they have given a table. This table gives an useful information. Whether it is fair, whether it is good, whether it is recommended or not. These informations are given. When you put F, it is fair. When you say it is NR, it is not recommended. You should not do this process at all. When you say it is good, G, it is good. When you say it is E, this is excellent. You have to select the process in such a way with respect to these materials, depending on this table. Right? NR means it is not recommended. Right? G means good, F means fair, E means excellent. Okay? And another this is the table which gives the filler metals. I told you so many electrodes are there, TIG fillers are there, right? Depending upon these base materials, you'll have to select the TIG or MIG wires. On certain category, we don't have the covered electrode. For some alloys alone, we have the covered electrodes. For example, aluminum brands, we have both. Whereas for manganese brands or bronzes, we don't have the covered electrode. We have only the wires. We have to go with the gas shielded process like TIG or MIG. Okay? This is the commercial name people used to call. Right? Sometimes they never call for this. They say phosphorus bronze, copper nickel bronze. Also, they have something like naval brass, no fail brass, silicon bronze, and so on. Right? Based upon this alloy content, electrodes are available in the AWS classification both for shielded metal arc wires also available, and you have to select suitably based upon the base material. And this all I wanted to finish up this lecture. Any doubts are there, you please ask. So otherwise, we can hand it over the session to the next faculty.
Thank you, sir. Thank you for your wonderful session, sir.
Okay. Doubts இருந்தா கேட்டுக்கோங்க, எதுவும் இருந்துச்சுன்னா நீங்க கேளுங்க. Otherwise, you can.
Yes, sir. Yes, sir. Yes, sir.
Move to the next faculty.
Yes, sir.
I think already.
Same link தான் sir. அதுலயே நம்ம
Mr. Parameshwaran, I think will handle.
Yes, sir. Yes, sir. Sir, 1 minute. Break up. Sir, now we can give break, sir. Break கொஞ்சம் விட்டுட்டு அதுக்கு 11 o'clock ஸ்டார்ட் பண்ணலாமா சார்?
10:45 வர சொல்லிடுங்க மகராஜன். ஃபேக்கல்டி வந்துட்டாரு. 12 minutes 10:45 வர சொல்லுங்க.
சரிங்க சார்.
We start the session by 12:40 will complete it. நம்ம டைரக்டா பண்ண மாதிரியே. Okay?
சரிங்க சார்.
Break up to 10:45.
10:45 வர சொல்லிடுங்க சார். Okay, sir. Okay, sir.
Thank you.
Thank you, Rajshekar. தேங்க்யூ
Thank you, sir.
தேங்க்யூ
Thank you, sir.
தேங்க்யூமா.
சிங்காரவேலு,
சொல்லுங்க.
உங்க பேங்க் அக்கௌண்ட் நம்பர் அனுப்பிச்சிருக்கீங்கல்ல, இங்க இருக்குல்ல ஆபீஸ்ல?
ஆபீஸ்ல இருக்குன்னு நினைக்கிறேன், அவரை கேட்டு பாருங்க.
அவர் இன்னும் வரல.